Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. This is lecture number 24 and we enter into a new topic, and that is basically on heterostructures, which I will deal in the next lecture possibly. But to go into that level of heterostructure or understanding heterostructure, we have left one small topic, and that is basically transportation and carriers, which means that this lecture will be primarily looking into the types of carriers you have in a semiconductor, and what are the transport mechanisms and generation and recombination mechanisms which happens in a semiconductor. That we will be looking into in this lecture. So the outline of this lecture is give you an idea about drift current. We will look into diffusion current. We will also look into the total carrier current, right? And total carrier current we will look. We will have a look at displacement current, continuity equation, thermionic emissions, tunneling phenomena, and then we will recapitulate later on, right? Now, why this is important from the point of view of any not only heterostructure but for any device current is that we should know how the currents are being formed, which is already known to you in a MOS device, and then on what factors does the current depend on, right? And that also we have seen in our previous statements that it depends upon many factors, and some of the factors are already mentioned in my previous lectures. So, we will start one by one and make it very simple. So, basics concepts will be clear to you, so that you can deal with this later on when you have some advanced topics related to this. What we are looking is basically the transport refers to the movement of charge carriers from point A to point B within the semiconductor, and there might be two reasons for that, right? One reason is you apply a bias, and when you apply a bias, be it positive or negative, there will be an electric field. When there is an electric field, there will be always a force acting on the particle. So, if you have an electron, then and if you have an electric field E, then you will always have a force acting on the electron because of the electric field in the direction opposite to the direction of the rising electric field, and therefore, it will move in the opposite direction, whereas the holes will be moving in the same direction. This is constituting drift, whereas diffusion will be more of movement from a region of higher concentration to a region of lower concentration. Just to showcase what I was talking about, basically drift is in the MOSFET inversion region. When you apply a VD, that is a drift. But in a PN junction diode, when you do not apply any external bias, you still have a diffusion current by virtue of the fact that there is a large difference in the concentration of charge carriers across the metallurgical junction. That constitutes a diffusion current. If you look at that to two particular points or two important points, the carrier transport can be broken up with electrons obviously in the conduction band and holes in the valence band. So, if you look from the band diagram point of view, then we have already discussed in our previous lecture, just to corroborate it. So, if I have this conduction band and the valence band, we all know that electrons are free in the conduction bands and you will have holes in the valence band. This is the lowest energy of the conduction band, and as you move to the top, the energy goes on increasing. So, basically when you give a bias and you have a drift, the electron gains energy, and actually in the band diagram level it shifts to the top, right? And obviously when it moves, its kinetic energy increases, however its potential energy remains the same, right? And therefore, you will see what it will move across in this manner. If you give an external energy source, say for example you are giving a photon, and therefore this will force this electron to move again to the top direction. So, both electrons and holes will behave in the opposite sense. However, if you remember correctly, effective mass for electron is much smaller than the effective mass of holes, and therefore, we say that the mobility of electron is relatively larger as compared to mobility of holes. Just keep these two basic entities in mind for the functionality of the carrier transport. With this, let me come to the drift. We already know this. I will quickly go through the concept here, that if you have an electric field present, it will control the flow of the current in the devices, it will flow the control of the current, and therefore, the charge particle will move under the influence of an applied electric field, right? Under the applied electric field, there will be a flow of charge carriers, right? However, when you look at electron drifting in a material, obviously these electrons will not be drifting like in a straight line. They will always drift such that there will be multiple scattering with the ions and with the particles of the device itself. And when it does that, it starts to scatter from its mean position, right? So when it does a scattering from its mean position, its mobility drops down, right? And scattering related mobility, which is always available to us. And higher the velocity, more is the probability of scattering, and therefore lower is the mobility which you will get. So if I plot typically in a silicon, if I plot say electric field versus velocity, and this is basically my drift velocity, then you will see it something like this. The graph is something like this, which means that as the electric field increases, the velocity also increases. As the velocity increases, the scattering mechanism also increases. A time comes when they all become equal to each other, and then you see a sort of a taping down action, and then it finally velocity actually saturates to a fixed value. It is almost like raindrop falling from the sky. So it starts from a low velocity, obviously zero velocity, but as it reaches towards the earth because of the gravity, it reaches to its critical velocity. Anything larger than that is not possible. Why? Because as it starts moving downwards, there is a drag force acting upwards. Now when the drag force becomes exactly equals to the downward force pulled by the gravity of the earth, its velocity becomes constant, right? And therefore there is no acceleration available to you. Exactly the same thing happens for a transport mechanism in case of a drift mechanism in case of electron in a semiconductor. Now let us look at the drift current, the charge per unit time crossing an arbitrarily chosen plane of observation oriented normal to the direction of the current flow. This is very important, that how do you define therefore a current? Current is charge flowing per unit time per unit area normally to the surface is basically defined as my drift current, right? If it is not normal, then you need to take a theta term to normalize it across the dimension of the plane, and it is charge per unit time. So you see what is the importance of drift velocity? It's charge per unit time, which means that if the drift velocity is large, then per unit time larger number of charge carriers will pass through, and as a result your drift current will be also very large. So if you look very carefully, we write the drift current as this quantity. It is Q. Q is the electronic charge or hole charge in this case, P is the number of holes, V, D is the drift velocity, and A is the area under consideration. So now if you take A to the this thing to the denominator, I am left with Q P into VD, and this IP by A is defined as JP drift. JP drift is defined as the current density, right, and its magnitude is current per unit area, right. And many a times you will see when we move across is that you will find current density to be basically per unit area, which we are trying to do, and this is current I by A. So current per unit area is there. Now I had already discussed with you that if you look very carefully, this expression Vd equals to mu P times E, where did I get it? I get it from this graph only. So mobility is defined as velocity per unit electric field, which means that if you find the slope of the graph, then del V and del E is there. So I just find out del V and del E, and you take a differential of that and you will get mobility. So till this much point the mobility is constant, right, and that is what I have shown here. So for small to moderate values of electric field, the measured drift velocity is directly proportional to the electric field, and this is exactly coming from this graph actually. From this graph, if you see, V is linearly proportional to E, and as a result Vd is equals to mu P into E, which you get, where mu P is the mobility of holes. So all these discussions are with holes, you can as well do it for electrons. Only the change with electrons will be the direction of the drift velocity for electron will be just opposite to that of holes when you consider it to be a semiconductor, right. Opposite direction movement will be there. And please understand, this is only for small to moderate values of V. For large values of V, this relationship does not hold good, right, and there will be a non-linear profile, and then a saturated profile will come into picture. If you look here on this is both log scale, this is log scale. So both your electric field is also log and your velocity is also log, right, and this is for gallium arsenide, electrons in gallium arsenide, this is electrons in silicon, and these are holes in silicon, right. And so you see, as you start increasing the electric field at a very low value, the velocity increases also like this. So what we see is, for the same increase in the electric field, we get the same increase in the velocity as such, right. It's almost the same. So it crosses through these regions in a very even fashion, and that's the reason we say that the mobility is constant for moderate to low values of electric field. However, for high values of electric field, you see a saturation tendency comes into picture. There is a saturation tendency. However, if you look very carefully into this domain, you will see that how do you find out the mobility? You just need to find out the slope of the graph. Now, that's what I have shown, that Vd is proportional to E. However, you see, let me take 10 to the power 3 volts per centimeter as the loop line. Let me remove it, and let me draw a straight line crossing these three regions. So this is one, this is another one, and this is another one. If you look at this straight line, then when your electric field is 10 to the power 3 volts per centimeter, then the velocity of the charge carriers of the holes in silicon, right, the holes in silicon is somewhere here, which is say 10 to the power 5, and then you have 1, 2, 3. So you have 3 into 10 to the power 5 approximately centimeter per second. Then if you take this one, this is 10 to the power 6, this is around 1.5 into 10 to the power 6 centimeter per second. If you take gallium arsenide, it is about 8 or 9 into 10 to the power 6. So you see, for the same amount of electric field, the velocity for holes is the smallest, followed by electrons both in silicon, and then the electrons in gallium arsenide is the highest, which effectively tells me that the mobility of electron in gallium arsenide is the maximum. So typically we therefore come to the point that the mobility of charge carriers in 3-5 semiconductor is the highest, and that for silicon in electrons is lowest, and holes in silicon is the lowest. So the middle one is basically the silicon electrons, right. And these are all very high purity silicon and gallium arsenide with no impurities. So there are no extra scattering mechanisms available within the device itself, and that is the reason you see they are almost in a manner shown here. However, if you go for a very high electric fields, gallium arsenide velocity actually drops down below silicon even, right, and that happens around more than 10 to the power 5, somewhere between 10 to the power 5 and 10 to the power 6 volts per centimeter. So somewhere here you see you have a crossover point taking, and then this gallium arsenide starts to shift back. So therefore, if you take the dimension of gallium arsenide, silicon and everything else, you will see that gallium arsenide gives you the largest mobility in the case. Now let us come to the diffusion. Diffusion, all of you are aware of, movement from region of higher concentration to region of lower concentration. So very simple and straightforward. If you look at this graph here, we have larger number of holes on this side and we have lower number of holes on this side, and therefore there will be a diffusion of the charge carriers from a region of high concentration to a region of low concentration. There will be diffusion taking place here, and you very well know that the direction of current is exactly the direction of the movement of the positive charge carriers. In this case it is holes. You can say that this will be the value of Jp drift, or hole current density will be in the same direction as the direction of the holes. However, when you take up an electron, then electron has got this side higher concentration and this side a lower concentration. This has got a higher concentration. Then the diffusion takes place from a region of higher to lower, but the conventional current will be the opposite of it. So I get Jn diffusion in the direction which is moving from a lower concentration to a higher concentration, right. And we are assuming that when you do a macroscopic particle, we assume that at any one point of time, half the particles move from left to right and other half move from right to left across this junction. So if there are 4 particles here, 2 will be moving to the right and 2 will be moving to the left, right, as you move from a region of higher concentration to a region of lower concentration. We will be not deriving all these quantities, you can find it in the book. So when we find out the diffusion current, let me first find out the diffusion current and then we will come to the assumption. The diffusion current is given by this, is given by Q into diffusion constant. This is known as dP and dN are the coefficients, electron and hole coefficients, right, diffusion coefficients. So I get Q into dP into del of P, right. Similarly Q into dN into del of N, right, and we write down this as there. So we see with spatial, so del of P and del of N is the spatial distribution of electrons and holes within the region. Assumptions are that the electron collisions within the depletion regions are neglected. the carrier concentration at x equals to W and x equals to 0 are unaffected by the current flow, which means that when current is flowing, the carrier concentration we assume that is not changing at a particular point, and the impurity concentration of a semiconductor is non-degenerate, which means that it is very low. So, you have very low impurity concentrations and they do not act anyway in scattering the charge particle from one point to another, right. However, we end up therefore having these two expressions here, which is the diffusion current for both p type and n type semiconductor, right. And del of p is basically the space charge distribution of the holes and space charge distribution of electrons respectively. So, if you look at the current equation therefore, then the electron and hole currents per unit area in a semiconductor, if you take the current density, then it is given by the drift component here and the diffusion component here, right. At this stage we are not taking into consideration the sign of the charge particle as such, we are just assuming that the basic physical quantities are being met. And if you look at the first term, it depends upon the mobility of the charge carriers, P is the number of electrons or holes and E is the electric field. On the right hand side you see diffusion constants here, and then these are the phase derivative of the charge particle, and this gives me a relatively a good value of Jp and Jn, though some corrections are still required in these values of Jp and Jn. Let us look at the dielectric displacement current. So, you see it is something like this: when you have a capacitor, how do you say that the current is flowing through a capacitor, right? Because in the capacitor the part between the two plates of the capacitor is still viewed as a dielectric, and therefore electrons cannot flow through them. In order to substantiate that value of voltage, a concept of dielectric displacement current or a displacement current has been introduced, right, and that is given by ddt of capital D, the polarization which is happening. So, the way we look into it is, if we have two capacitors here, plates here, and if we apply a positive and a negative charge, then the polarity of the dielectric domains will actually be such that this side will have negative and this side you will have positive. The change in the polarization by application of an external bias will result in a sort of a dielectric displacement current which will be moving, right. This is not the actual current, but sort of a current. Then we write down the total current is equals to Jn, Jp and Jd. J and Jp are because of the drift, and diffusion, and Jd is because of the dielectric displacement current, right. These three things we are taking into consideration. I will just touch and go because you can refer to other courses and books for this, but I will go one by one. So, the first one is, these equations are known as continuity equations, and if you look at the process here, it tells me that the rate of change of electrons with respect to time is given by the rate of change because of drift, diffusion and recombination. Rg is recombination generation, right, and for other requirements. So, you see these are plus sign here, all are plus sign. For other recombinations means, let us say you have a photo generation mechanism or radiation coming into picture, all those are taken care by the fourth term, and just by recombination generation you have the third term coming into picture. This is for the variation of electrons with respect to time. This is for the variation of holes with respect to time, and the same equation is valid for that. Now, we have already seen in our previous discussion, and we can actually do it. These two equations, which is basically drift plus diffusion, is given by 1 by q del of Jn, and this is minus 1 by q del of Jp, right. And please understand why is it minus for holes whereas it is positive for electrons, right, minus with respect to Jn and Jp. So, why this is negative, why positive, I will leave it to you for explanation. We can write down therefore del n of del t equals to this quantity, this takes care of both drift diffusion minus the recombination and generation. So, when you recombine, you are actually reducing the number of carriers, and that is the reason it is negative. When you are generating, since you are adding large number of carriers, you get a positive sign here, right. Same thing is for holes, but the holes will have a negative sign here, right. They will have a negative sign here, and there will be a negative and positive sign given at this particular point. Recombination, as you can see therefore in the right hand side, if you look, are all covered with negative sign, and generations are all covered with positive sign, because generation adds carriers and recombination actually starts to remove carriers from the system. Recombination of electron and hole actually. Then there are other methodologies by which we go ahead, and that is thermionic emission and tunneling. Now, Thermionic emission is very simple and straightforward, and I will show you to it. So, if I have a band diagram and if I am able to give an energy equal to this much, then I will have a jump and there will be a free electron and a hole being created, right. This is basically a thermionic emission, right. This is because of thermal perturbations or thermal inputs from an external source. And typically these thermionic emission occurs at very high temperatures with and there is a large band discontinuity. We will come to this later on when we discuss heterostructure, but even in silicon it is possible to have it. But then you have to ensure that the temperature when it goes very high, it should not melt the device or should not make the device go wrong before it goes for thermal emission, right. So, that is one important point. The last point is tunneling. Tunneling is basically the quantum mechanical tunneling which happens between the regions where the barrier height is very high, and therefore, you ideally won't expect an electron to go from one point to another, but because of quantum mechanical effects there will be a tunneling between point A and point B, and typically this happens for a heavily doped junctions. We will discuss it later on in much more detailed manner. I have already discussed with you recombination of electrons and holes. When they recombine, you are basically releasing energy, and the release of energy is through a photon release, right, or through phonon emission. Phonon emission is a thermal emission, so that the lattice temperature actually starts to rise, right. So, I have an electron and hole available with me. I have an electron and I have a hole. When they recombine, they give out, it is an exothermic reaction, they give out delta heat, and this heat might be going to lattice to raise the temperature of the lattice. This is known as phonon, or it can go to photon, and this is where you will get photogeneration, right. So, you will get photogeneration, and this might happen, right, and there will be a this thing. Similarly, the generation mechanisms can have an impact ionization. Impact ionization basically means that when the electron strikes stationary silicon particle, it might radiate electron hole pairs in a larger sense when the energy is large. So, let me finally come to the equations which you need to remember for this lecture at least. Is the first, the continuity equation. These are very important equations. These are very important from device characteristics point of view. This, though I have not taught to you about the minority current diffusion equations, but have a look into it and you will get good books to go through it once. This relates how does minority current carrier contribute to the diffusion current. And finally, we look into the Poisson equation, and this Poisson equation is the very standard way of looking at it, that del of E equals to rho by epsilon. Rho is the net charge, and it comes from the Gauss law. The Poisson equation comes from Gauss law. So, as a student, the best part to remember is the first equation, the continuity equation. The second part, you might keep it into your mind, might be useful for you in a longer run, but these are all second order effects, diffusion effects. The first one is basically the continuity equation, which you should remember when you are actually doing a course on a device physics course. These are already defined to you, right. We have already defined, this is basically these two are because of electron and hole drift plus diffusion, and this is the displacement current which you see. Then this rho is the net charge, right. We have already told you this is the net charge. Net charge actually consists of free holes, free electrons, donor impurities who have given their electrons, so they are in ionic form, and acceptor impurities who have accepted electrons and converted themselves to a negative charge particle. And if you multiply that with Q, you will get the value of rho. Rho is therefore the net charge available to you, and the first two equations I have already discussed with you are because of the electron and hole diffusion constants, right. The last two slides gives you a comprehensive knowledge about the equations which you will be used when you will be doing the transport phenomena in a silicon. So, let me recapitulate what we did for this whole lecture. We looked into the concept of drift, right. We looked into diffusion, right, and then we understood the difference between drift and diffusion, and then we looked into displacement current. And then what we did was we gave you an idea about the drift, diffusion, we gave you a displacement current, and then we gave you an idea about various equations of drift and diffusion, right, and also of displacement, and how these equations are valid and where they are valid. And so, these four things were studied in a detailed manner as far as this lecture was concerned. I hope you enjoyed the lecture. Thank you very much.